The thing that is most challenging about the work that I do, or the work that any of the research scientists here at NIST do, is that we don't know what we're going to learn. And that's also the thing that makes it so satisfying and so exciting. We're learning new stuff every day. We go into the lab and we don't know what's going to happen. And lots of times when we see something that happens in the lab, something that we didn't expect, we don't know why it's happening. We have to figure it out. It's all unknown. It's all at the frontier. So we've got to find our own way. Nobody's made a map for how we're going to proceed. We've got to figure it out. That's a challenge, but it's also an adventure. And as research scientists, we get to participate in that adventure every day. One of the things that was really important for me in getting started with laser cooling is what had been done at NIST by Dave Wineland. Dave Wineland came to NIST a few years before I did, in the 1970s. I came in 1978. And in the year 1978, before I came to NIST, something really important happened. Dave Wineland and his colleagues published the first paper about laser cooling. They had demonstrated that you could shine light on something and make it cold. Now, first of all, that sounds ridiculous. Usually you figure you shine light on something, it's going to get warm. They figured out how you could shine light on something and make it cold. And there was two really important parts about Dave Wineland. In 1975, when he was at the University of Washington, he came up with the idea for laser cooling. He came to NIST and he put that idea into practice. He made it work. I read that paper and I thought, that's really cool. I wonder if I could do that with neutral atoms. So we started to cool down atoms by shining laser beams in from every direction. And the way this is supposed to work is that you tune the laser beam so that it's a little bit lower in frequency than what it should be for the atoms to absorb the light. Now, if the atoms absorb the light, they're going to get a push. Now, what you want to do is to push on the atoms in the opposite way from the way that they're moving. Well, if the atoms are moving this way and the light's coming this way and the light's a little bit too low in frequency, then because of the Doppler shift, the atom is going to think that the laser beam has a frequency that's a little bit higher, which is to say closer to the frequency that it wants to absorb. So it'll absorb it and slow down. If the atom is moving the other way, it sees the frequency being wrong, and then it's not going to absorb it. You see, if it did, it would speed it up. So this is the basic idea. And based on that, you can calculate how cold you should be able to get the atoms. We started to make these measurements, and it looked like the atoms were actually colder than was possible based on that idea. The work that Dave Wineland did, which led to the Nobel Prize in 2012, started the whole business of laser cooling. And it was his work that inspired me to get started in the first place. The work that I did, learning how to laser cool neutral atoms, atoms that don't have an electrical charge, learning how to trap them, learning how to get them down to incredibly low temperatures,
Och sen Bill Phillips,
formed part of the basis that allowed Eric Cornell out in Boulder to achieve this dream that Einstein had back in the early part of the 20th century, to make a new kind of a gas, a thing called a Bose-Einstein condensate. And that earned Eric Cornell and his colleagues the Nobel Prize in 2001. And we were all keeping in mind the mission that NIST has: make better measurements. Make the kind of measurements that are going to make a difference in science, in industry, in people's daily lives. So why are atomic clocks so important? I mean, who needs to know what time it is to the level of accuracy that atomic clocks give us? Well, we don't need atomic clocks to figure out when we're going to go to lunch, but we need atomic clocks for things like global navigation. The global positioning system, the satellite navigation system, relies on the fact that on those satellites there are atomic clocks, and those atomic clocks are broadcasting information about what time it is and about where the satellite is. When you receive that information in your GPS receiver, the GPS receiver figures out, based on those time signals, where you are. Now, those satellite clocks don't have laser-cooled atomic clocks in them, but on the ground, we have laser-cooled atomic clocks, like the atomic fountains at NIST, that are synchronizing all of those satellites. And they are being used to track where the satellites are. So having the very best clocks that anyone has ever had on the ground is making those clocks in the satellites work better, and that whole system working together is making the global positioning system work for us. So what's next? Well, now we're past the stage of figuring out how to make atoms really cold, how to trap them. What we're doing is using these atoms to do new kinds of things. We are using the atoms, these incredibly cold atoms, as carriers of information. Now, in your computer, in your iPhone, in your PDA, your CD-ROMs, information is stored as bits. These are the zeros and ones that we hear about, and those things are stored in some physical form. What we're using is single atoms, and the way in which the spin of the electron in that atom is pointing, one way or the other way, that's the 0 or the 1. But the amazing thing about storing information in an atom, in the electron, in the spin of the electron of an atom is, they can be 0 or 1. It can be pointing this way, or it could be pointed that way. But it can also be pointing both ways at the same time. Now, how's that possible? How can something be in two places at the same time? Well, it can't be in our ordinary world, but in the microscopic, the submicroscopic world of quantum mechanics, the theory that describes how atoms and electrons behave, things can be in two places at the same time. And that opens up an opportunity for information that is completely different from the kind of information that we're used to in our ordinary computers.